Hello students, so in this lecture we shall continue our discussion on matrix methods in geometrical optics. Previously in lecture number 283 we give introduction of the different matrices, and we uh, derived the following matrices. This is for translation matrix. It is given as 1 0 and d distance traveled by mu 1, and this is the refraction matrix given as 1 minus p 0 1, where p is the power of the matrix. Now we shall use these two matrices in finding out the system matrix for different cases. So we first start with the diffraction at a convex spherical surface. So in this case, if we have a spherical surface like this, and this is principal axis, so refraction is taking place, say, from here. The angle of refraction is I, angle of incidence, and getting refracted, so this is R. So this has got a refractive index of mu1, this medium. This is refractive index of mu2, and this is the incident. This distance is u, and this distance is v. So in a convex spherical surface, the radius of curvature is r. So the power is given as mu2 minus mu1 divided by r, and this is being used here in this power, and this is the power of the refracting surface. So we can write the system matrix in this case as S. So first there will be a translation from the object to the refracting surface, and that is given by as so this is mu2, this is inside the refracting surface, multiplied by the refraction matrix and multiplied by the incidence. It's multiplication of the three matrices, and ultimately for periaxial rays, so it will be lambda 2 x2 will be equal to the system matrix into lambda 1 x1, and for paraxial rays, x1 is equal to 0 and also x2 is equal to 0. So we obtain the relation. If we do the simplification, we get mu2 by v minus mu1 by u is equal to mu2 minus mu1 by r. Now the second case that we will take up is of a thin convex lens. Assume that there is a thin convex lens, and this is the object. So suppose action, and we get the image here. So this is the object, this is the image. we will consider this distance as d1 and this distance as d2. So d1 is negative and d2 is positive. R1 is positive and R2 is negative. These are the radius of curvature of the two faces. So these are as per the sign conventions that we initially discussed. So if it is from the left to right, it has to be a negative. From right to left, it has to be positive. So that goes for the same for the curvature. So if this is the case, then we can, if we assume that refractive index, this is the air, so having refractive index mu is equal to 1 here, and this has got refractive index mu. So we can write the power 1 for the first refracting surface as equal to mu minus 1 by r1, and for power 2 for the second refractive surface as mu minus r1 minus by minus r2. So the system matrix S is again, if we write it as minus P minus A minus T and C, so this will be equal to simply the multiplication of the refraction matrix of these two surfaces. So first it will be the P1 surface, so it will be 1 minus P2 0 1 multiplied by 1 minus P1 by 0 1. So by calculation what we get is the system matrix. We ultimately get S, that is V minus A minus T and C, we ultimately get as equal to 1 0 minus P1 plus P2 1 minus 2 minus P1 plus P2 into 1. So if we substitute, okay, so from here we get the following relationship. We get A as equal to P1 plus P2. We get B is equal to 1. We get C is equal to 1, and we also get D is equal to 0. So, and we also obtain the relation as BD2 plus A D1 D2 minus C D1 minus D is equal to 0. And if we substitute the values here, we ultimately get the final solution, final equation as 1 by D2 minus 1 by D1 is equal to mu minus 1 into 1 by R1. I did it freshly. Get 1 by D2 minus 1 by D1 is equal to mu minus 1 into 1 by R1 minus 1 by R2 is equal to 1 by F. This is the final equation. And if you consider a thick length, on the other hand, thick lens is characterized by translations. Previously, it was only two surfaces of diffraction, but it is now characterized by a translation. So again, there will be an object and which will undergo fraction inside the thick lens, and it will form an image here, say. So we take this one as a d1, this distance, this one as d2, and it will be same as in the previous cases. Only difference is that there will be a t involved here. So again we have power 1 for the first refracting surface as mu minus 1 by r, and power 2 will be mu minus 1 by r1, and power 2 will be mu minus 1 by minus r2, or it will write it as 1 minus mu by r2. So this is the matrix. We can write the system matrix S as equal to 1 minus P2 0 1 multiplied by translation 1 by T by mu 0 1, and lastly it will be 1 minus P1 0 1. So the equation will look something like this. It will be lambda 2x2, and it is equal to the system matrix S into lambda 1x1. So again we can write S as equal to B minus D minus A into C, and so what we get is the following thing. We get this one as equal to a very large quantity, which is minus P2 T by mu into T by mu into minus P1 minus P2 multiplied by 1 minus T by mu into P1 into 1 minus T by mu into P1. So in this case, this is the system matrix for a thick lens. Now here, if we assume that the thick lens, the thickness, if we reduce the thickness, we reduce the value of t tends to 0, then actually we get the following expression. We get as 1 0 minus P1 plus P2. So this is the system matrix for the thin lens that we derived previously.